Question number 5. Dihydrogen monosulfide and water are both covalently bonded molecules and have very similar shape, however very different chemical and physical properties. Dihydrogen monosulfide, H2S, is also known as rotten egg gas due to its pungent odour. Draw the valence structure for both of these and name their VSEPR shape. So what have we got? Water is, again, doing some basic working out here. Sulfur is, again, that. So therefore, they're going to have the same shape. You'll be familiar with water like that. Sulfur is this guy, and they are both V-shaped molecules. Okay, so if in doubt, draw out the Lewis dot structure and you can kind of come together with what the molecule will be, but that's what it's going to look like there. If I'll just go through that again, hydrogen, sulfur, looks like this because sulfur, again, is in group 1, 2, skip a few, 3, 4, 5, 6. Sulfur's in group 6, so therefore it's got your 6 electrons in the outside shell. So therefore a hydrogen is going to jump in here with a lone pair. Hydrogen's going to jump in here with an unpaired electron, and another one here brings you out with this structure. Give a reason why both molecules have a similar shape. Well, shape comes from the VSEPR rules, and it also is dictated by how many lone pairs and bonding pairs. Both have 2 lone pairs of electrons and 2 bonding pairs of electrons. You could also go down the route of saying they both have the same number of electrons in the outside shell of their central element. But basically we're looking at how many lone pairs of electrons we have within our molecule around our central element. Explain why H2S is a gas, yet H2O is a liquid at room temperature despite their similar structure. Well, this here is all about boiling points, all right, and melting points, which is all about properties. And properties equals intermolecular forces. So H2S equals polar with dipole bonds. H2O equals polar with hydrogen bonds. And H bonds are stronger than dipole. All right, so therefore we have that. Main thing is whenever you see things talking about states, it's to do with melting and boiling points. Their properties, okay, of these, and the properties come from the intermolecular forces that these molecules actually have. Question number D here. A chemist fills a syringe with 0.45 moles of dihydrogen monosulfide gas, H2S. Determine the mass of the gas. Mass of H2S equals number of moles times molar mass equals 0.45 times by, what's this going to be? That's 32.1 plus 1 plus 1, it's 34.1. Trusty calculator. 34.1 times 0.45 gives me 15.345 grams. Determine the number of moles of hydrogen present in the syringe. Number of moles of H equals, where are we? 2 hydrogens, so it's going to be 2 times number of moles of H2S equals 2 times, that's the grams, this is the moles, 0.45 equals 0.9 mole. All right, determine the total number of atoms in the gas syringe. Number of moles of atoms, so total number of atoms, so that means capital N of atoms equals N times Na. So I need to work out the number of moles of atoms. There's 3 atoms present here, so it's going to be 3 times the number of moles of H2S equals 3 times 0.45 gives me 1.35 mole, and then it's going to be 1.35 times 6.02 times 10 to the power of 23 equals times 6.02 times 10 to the power of 23 is 8.13 times 10 to the power of 23. And that, my friends, is the answer to that question. Going through it again and looking at it a bit slower, determine the mass, I write down my formula. I work out my mass is my number of moles times my molar mass. Take that in there, work out the molar mass of that. Gives me this. Number of moles of hydrogen, I write down the fact that I want to find number of moles of hydrogen. How is hydrogen related to this? Well, it's 2 times that because there's 2 hydrogens in every one molecule. So for every one of these, I have 2 hydrogens, so it's 2 times 0.45. Then I want the total number of atoms, so therefore I need to know the total number of mole of atoms, which will be 3 times that. And then I'll times that by Avogadro's number, because that's going to find me the individual number of atoms from how many mole I have. And that, I think, is the... Oh, there's another question. We're going to do question 6 next.